What if I told you a wave and a particle are the same exact thing? Well, you think this is crazy? Let me show you. So in the early 1900s, physicists had a problem. Imagine there are two walls. One right here, one right here. Imagine the picture here, and he's throwing baseballs at random places. Right, so some here, here. Now, none of these baseballs go to this wall, because this wall blocks all of them. If you put a slit here, then it'll show a pattern in this wall, like this. If you put two slits, it'll end up like this. Now this seems to agree with everyday experience. It's pretty normal. But what if instead of baseballs, we shine a light? What shows up is this. This is called an interference pattern. And the reason it happens is because light is made up of waves. Now imagine this is one light wave. Let's say we have another light wave. Notice how for every rise here, there's a drop here. And these rises and drops cancel each other out and make like this. This is called the destructive interference. Now what if we had this kind of wave? And the other waves like this. The resulting wave will be even bigger than both of them. This is called instructive interference. So what did this have to do with the so-called famous double slit experiment? Well, see here. When you shine a light, here, in some spaces, they cancel each other out, so there'll be nothing in the wall. Some places, though, they build each other up, so there's more, and it creates the interference pattern. Now this is all great, but in the 1900s, physicists did the same thing, but with electrons. And what they discovered was that electrons also made an interference pattern. But this shouldn't be happening. Electrons are particles, not waves. How do they make an interference pattern? This led physicists to come up with the wave-particle duality, which basically says that particles and waves are the same thing. Now you might be confused right now, like particles and waves aren't the same thing. How does this work? What happens? Electrons have a wave function, so they're waves. But when you measure them, they turn into a particle. The wave function collapses and turns into a particle. No one knows why this happens. This is one of the mysteries of quantum physics. So you see in the double slit experiment, the electrons have the wave. And here, because of the interference, the resulting wave is kind of like this. Right? And these give the probability of where the electron will be. So this here, since it's higher, this has the most probability that there will be an electron here. So you see, after repeated experiments, the interference pattern will start to build up. So light too is also both a wave and a particle. You know the light is a wave. But you also heard of a photon. What is a photon? A photon is what you call light when it behaves as a particle. Sometimes it behaves like a wave, sometimes it behaves like a particle. In the photoelectric effect, This is actually how solar panels work. Imagine this is a solar panel, right? It's the photon. A photon of light comes, there's some extra electrons here, and it bumps the electron, and it creates an electrical current, which creates electricity. Now, the wave-particle duality may contradict with ordinary experiences, but it's part of the basis for quantum mechanics. So, to summarize what we just learned, everything either can act as a particle and a wave. This is known as the wave-particle duality, and it forms the basis of quantum mechanics. I hope you learned something today, and I want to thank you for watching.